Unit 4 homework FRQ question 2 is a particle motion problem again, but in this case we're moving along the y-axis. So instead of describing it as left and right, we have to describe it as up and down. The first one is to show that we end up with this function as velocity here, right here. So that's just taking the derivative of the position function, which is given up at the top. Don't forget you need to use the product rule and the chain rule. I'm sure in the rubric it'll tell you that you know they're looking for 1 point is definitely using the product rule. The second point is to use the chain rule here. This part is the chain rule, by the way, which kind of works out conveniently because they cancel each other. The negative t or the t squares end up canceling each other out, and we end up, so we have the first, that was t squared, times the derivative of the second, that's all of this one, where the green part is the chain rule being used, and then the second times the derivative of the first here. And then do a little simplification, and we've shown that v of t is equal to what they wanted to. Now let's say you can't get that. If you have to use v of t somewhere else, then you use the formula they give you. Don't use your own incorrect formula. So part B is very similar. We had this on one of the progress checks, you know, where is it moving toward or away from the origin? But in this case now you got to describe the motion as up and down rather than left and right. So we need to find the position at 4 over pi, where you just substitute it in and show the substitution. The key is you need to tell us whether it's positive or negative. That's the key. So you don't have to simplify all the way. I'm just end up with whether it's positive. When I substituted in y of 4 pi into the original position function up there at the top, this is what I ended up getting. I know tangent of pi over 4, because 1 over t is the reciprocal of 4 over pi. So it becomes tangent of pi over 4, which is 1. And the square of 4 over pi is 16 over pi squared. So the key is that it's a positive value. And then with v of t, look, you're being told in part A what v of t is. So like I said before, even if you made a mistake and you can't end up with the same v of t, you got to use the v of t they gave you and substitute into that. And once you 2 times the t is 4 over pi, tangent of 1 over of t, that means take the reciprocal of 4 pi, so that's pi over 4, which is 1. And then the same, secant of pi over 4 ends up being square root of 2. So when I square that, it becomes a 2. So 8 minus pi over 2, or 8 over pi minus 2. What I did just for myself to figure out if it was positive or a negative number here is I got a common denominator. And I know that 2 pi is around 6.28. So 8 minus 6 point something in the numerator is going to give me a positive over pi, which is a positive. That's how I knew it was a positive without actually going all the way to the end. So my explanation is going to be, since the position at 4 over pi is greater than 0, the particle is above the origin, so don't say to the left or right, but above the origin at t is equal to 4 over pi, and since v of 4 over pi is also greater than 0, the particle is moving upwards, which means that the particle is moving away from the origin. The velocity of the particle at t can be written as follows. Find v of, now here, by the way, there are 2 possibilities. That their intent, you want to find the derivative as t, no, not the limit as t approaches infinity of the velocity function. The intent is for you to use L'Hopital's rule. I can tell by the question. I can tell because I get a 0 here and a 0 here, and you're finding a limit, and the limit question is like at the bottom, like the last question on it, or the last part of the question. So the intent was L'Hopital's rule, but you could also use temporary substitution if you wanted to in this particular case. So here, And then maybe I could have like it justified it by L'Hopital's rule there. So either way, but the intent is really to use L'Hopital's rule. So we'll stick to that. So what I wrote here is that I rewrote the limit as two separate limits, because the one that's highlighted in yellow is going to be L'Hopital's rule, and the one that's not highlighted we can just do regularly. So I know that the limit as t approaches infinity of secant squared of 1 over t is going to be the same as secant squared of 0. Secant of 0 is 1, squared is 1. So this part of it, this part of it is equal to 1. So I'm going to write that out here. And then I'm going to just deal with this limit inside the parenthesis, if you see that. And I changed over to red. For me to use L'Hopital's rule, I have to establish that it applies. So I need to take the limit of the numerator, that's this one here, and the limit of the denominator, that's this one here. I have to show that each of them are equal to 0 or both of them are approaches infinity, and then state L'Hopital's rule applies. And then we can take the derivative of the numerator and the derivative of the denominator. And in this case, it works out nicely. The derivative of the numerator using the chain rule ends up being 2 secant squared because of tangent. The derivative of tangent is secant squared of 1 over t. And then times the derivative of the interior 1 over t, that's t to the negative 1. Using the power rule, I get negative 1 over t squared. But you get the same thing in the denominator down here. So when you take the derivative of the denominator, it's t to the negative 1. When I take the derivative of that, it becomes negative t to the negative 2, which is 1 over t squared, and that means these two things cancel each other out, so we end up with just 2 times secant squared of 1 over t. And as t approaches infinity, 1 over t approaches 0, so we end up with 2 times secant squared of 0, which we already found out was equal to 1. So it becomes 2 times 1 minus 1, so the whole thing gives me just a 1. And the alternative is to use temporary substitution and then use L'Hopital's rule for this part here. So very similar. You would just do it slightly different.